Hello. Today we kick off our segment on quantum mechanics with the discussion in the university level physics relating to the linear vector space, and thereafter we'll be also discussing the Hilbert space and the various characteristics that it possesses. Uh, so we'll brief something on the Hilbert space and followed by the wave functions as well. Now, the linear vector space is basically it is composed of two sets of elements. So these two sets of elements that we deal with in linear vector spaces are the vectors and vectors as in case of psi, phi, chi, etc. and the usual notations, and the scalars are some constant values, probably A, B, C, like that. And they usually are associated by two algebraic rules, with the rules being the addition and multiplication. The addition carries the cases of commutative, the commutation property, also the associative, the neutral characteristic, as well as the inverse. Also, in case of multiplication, the characteristics that are associated are the distributive, the associative as well, followed by unitary characteristics. Now, these are some of the cases that we come across in the linear vector space. We have already dealt with the linear equations and the vector space, which is defined by linear characteristics having the vectors and the scalars following these rules uh, in them, constitute the linear vector space. Now, the Hilbert space is a linear vector space. So a Hilbert space, as I mentioned, is a linear space. And also, it has a defined scalar product that is strictly positive. Now, the scalar product of, say, we have the cases of psi and phi, that is equal to the complex conjugate of phi and psi. Now, the scalar product of phi with psi is linear with respect to the second factor. If we have psi to be equal to a psi 1 plus b psi 2, so this is a linear combination, as you can see, with the scalars and the vectors associated in that. And if we have the psi of that form, then we have phi taken with a psi 1 plus b psi 2, that is phi psi, to be equal to a phi psi 1 plus b phi psi 2, the scalar product that we see over there. And it has, so this is linear. So psi is a linear, the scalar product of phi. with psi is linear with respect to second factor, where the psi is the uh, second factor in this case. Now, if we have the case of first factor, it will be antilinear. So if phi is of the form a phi 1 plus b phi 2, then the scalar product will be antilinear with respect to the first factor. That is a phi 1 plus b phi 2 product, scalar product with psi is equal to the conjugate phi psi plus b star conjugate, that is phi psi. This is obviously phi 1. And also for the scalar product of psi with psi, we have the square, it is represented like this, to be greater than or equal to 0. So this is the case where the case of the defined scalar product in case of the elements present in the Hilbert space, constituting the Hilbert space, and they are strictly positive, so we have the value to be greater than 0 or equal to 0. Now all of these explanations that you have over here, they can be related to the three-dimensional vector space that we usually consider. Now if we are to, just like that, if we are to consider the dimension and the basis of the Hilbert space, then we must consider the cases where the vectors, say the vectors that make up the space, that constitute the space, are supposedly phi 1 through to phi n, and they are linearly independent if and only if the solution to the equation, that is ai phi I, where I is taken from 1 to n for n vectors associated that we have just given, that is equal to 0, is having a solution of the form a1, which is equal to a2 right up to an, is equal to 0. Now, in that case, they are linearly independent. But if the case may be that phi n is represented or expressed as a linear combination of a given vector, that is let us say of the form where we are taking it from I through to n minus 1, ai phi I plus n is over there, so n cannot be taken, so this will be taken from I is equal to n plus 1 to the final value n for the n space phi I. Now if that is the case, then the set is going to be linearly dependent. Just as in case of the three-dimensional orthogonal coordinate system, if we are considering the vectors along the x, y, and z axis, they are linearly independent because one of the vectors is not represented as the combination of the other two. So we can take the example of that space and that will help us in considering the situation over here in the Hilbert space. In fact, Hilbert space, that is also three-dimensional Hilbert space, the vector space, that orthogonal vector space that we consider in the in the higher secondary physics that we have studied so far. And therefore, what we can say is that the maximum number of linearly independent the maximum number of linearly independent vectors that we come across a space can have gives its dimension, just like the three-dimensional vector space, the orthogonal coordinate system. And also supposedly we have an n-dimensional case that we had just mentioned. We can say that it has a basis which is the maximum possible linearly independent vectors belonging to that space. We can, however, consider a few examples with relation to what we have just studied, how the linear dependency and independency works. Well, we can, for example, we can check the linear dependency of given set of coordinates. Let's say we have with us A is equal to 300, B is equal to 020, we keep it as -2, and we have C vector to be equal to 0 0 -1. These are the defined coordinates that that they have, the vectors that is. Now for a combination of them that we have considered, for the case of A1, a scalar multiplied to A, and A2 another scalar multiplied to B, plus A3 multiplied to C. In case we are taking it to 0, what we are ending up as 3A1 taken in the x direction for the first coordinate, and 2A2 we are keeping it to the three-dimensional space, and finally A3 in the k direction, that is in the z direction, that is equal to 0. Now we have 3A1 supposedly to be equal to 0, and so there also -2A2 can be taken as 0, and -A3 can be taken as 0. So we have A1 to be equal to A2 to be equal to A3 to be equal to 0, and hence this is a linearly independent. Now if we take the other way, the example, that is, let's see if we can express the linear dependency in any case. So we have A to be equal to 6 minus 9 and 0, and B to be equal to -2 3 and 0. So here if we are taking the A1 and the A2 constants to be multiplied to A and B, so we have A1A plus A2B to be equal to 0, then we get A1 6 I cap, which is the first term, minus 9A1 J cap, the second term here, which is present in this case. And for as for b, we have minus 2a2 times of I cap plus 3a2 times of j hat to be equal to 0. Now if we just rearrange this, we get 6a1 I hat minus 9a1 j hat to be equal to 2a2 I hat minus 3a2 j hat. And just a bit of multiplication will help us. If we multiply a2 onto the left hand side, that is 6a1 I hat minus 9a1 j hat, and we multiply 3a1 onto the right hand side, 2a2 I hat minus 3a2 j hat. Now in this case, what you can see is that both the sides are completely equal, and so in fact in the previous line itself we have a1 on one side and a2 on the other side, but this is a clearer picture with the multiplication done and dusted. So the vector can now be expressed in the form of one another, and hence we have this to be linearly dependent. So we got two cases where we first obtained the case of linear independence, where the vectors or the constants that the solution that we are ending up, they do not depend on one another, and here the solutions are depending on one another. So we have the case of linear independency over here and the linear dependency in this case. We can consider many more such cases where we can easily determine the case of linear dependency and independency. We would like to end this short introductory video on Hilbert space with the connection to the wave function. Now wave function is a square integrable function. Now as for the scalar product of two vectors that we have psi and phi, supposedly we have them to be denoted in this form: the integration of psi, its conjugate with phi dx. And if in case this diverges, then the scalar product won't exist. So in order that the function space possesses a scalar product, we must select only those functions for which this product psi with phi is finite. Now psi x is square integrable if we have it of the form psi scalar product with psi as psi of x squared dx and is finite. If this is finite, then the space of a square integral function will possess the property of the Hilbert space, and the dimension of the Hilbert space, however, of the square integrable function, that is the wave function, is infinite, of course. So this is more or less a brief introductory video on the Hilbert space and the wave function or the vectors that are associated in it. We will continue with this segment related to Dirac notations and their various properties in the upcoming videos, and many more to follow. Till then, thank you for watching.